Welcome everyone. My name is Taras. I'm a PhD student at Robotics Perception and Learning Lab. And today I would like to share with you some bird overview over my research. A lot of research which is applied in robotics is first applied on virtual agents. And so that's where my research lies. I'm focusing on virtual agents right now. And the title of my work, and on my PhD as well, in a way, is that agents also need to gesticulate. It will become more clear as we go. So the outline of this talk is like this. First, I will tell you why I do what I do, then how I do it, and finally, some cool and exciting results. And first of all, I want to tell you, robots are coming. There are going to be more and more robots in our environment. And we are going to interact with these robots in our day-to-day life in various scenarios. And that's why it's quite important how we interact with them. And for example, we expect from a social robot more than we do from a statue. We expect social robot to move, moreover, to move in a natural way. And since for us human, our communication is to big extent non-verbal, that's why robots also need to be able to express themselves non-verbally through body language. And in this case, I mean gesticulation. And I'm not the first one tackling this issue, so I want to give you a broad overview of the field. So historically, a few decades ago, people have been developing those methods for gesture generation in a rule-based way, as a system with many if-else cases, many conditions, and so on and so forth, designed completely by engineer. And you can imagine this is not really scalable, and it cannot represent all the possible gestures we humans do. So there has been a shift, especially recently with the deep learning wave, to the machine learning-based approaches, where system is learning how to gesticulate from demonstrations, from the example of human. So in this case, they took TED videos, and they learn a deep learning-based model to take speech text as an input and produce motions as an output. So they give it lots of examples of human gesticulating, and eventually the system learned to gesticulate. And then they even applied it on the humanoid robot now. So this sort of approach provides much higher adaptability. It also gives variability of gestures, but it comes with the price of explainability. This sort of system is not able to explain why it is doing this or that gesture, but I believe that's not a problem, because we cannot explain our own gesture either. So why would we need a social robot to explain their gesture? So I think that's a fair price. And so the task I consider is taking an audio signal as input. We want to generate a sequence of gestures as an output. And then we apply some sort of system, which I denote here as a black box, because we don't really care much what's happening inside, as long as it produces good-looking gestures. And the question is, of course, what kind of system should we apply? And before I go into my system, I want to give you a broad overview of what machine learning actually means. So in this setting, we have some sort of model, which would have some parameters for a specific task. And then this model would receive input. In our case, input would be an audio signal, right? This would get audio signal, and it would try to produce output to predict what kind of gestures have I done while saying this audio signal. And then we have in our data set the output, the correct gestures which I actually have done. And then we can compare the prediction with the true output. And we can calculate an error, the difference between what model predicted and what the reality was. And based on this error, we can update the model. And then it would receive next input, produce next prediction, compare with the actual truth, get an error, and update, and so on and so forth, until it is able to predict reasonably well all sorts of examples that we have. So this is a general overview of what machine learning usually means. And now in my framework, looks like this. We have a speech, and we want to generate gestures. And so we go through the speech with a sliding window every time taking a window of speech features and pass this window through the machine learning model called recurrent neural network. And then this model is producing the corresponding gesture for this frame. And then we slide this window over the audio, producing pose frame by frame. And then the sequence of those poses is becoming a resulting gesture. Are there any questions so far? Yes?
Is it the same recurrent neural network that you're using for passing the gestures?
So all those recurrent neural networks are the same, yes?
Yes.
Yes.
And don't you get some kind of discontinuity at some point when you pass the signal? Because it feels like, yeah, you have the frame, and then at some point some error happens and you will do a weird gesture. How do you control that?
Well, good question. So there is no explicit constraint on the output. It's produced frame by frame. The constraint is happening implicitly through the input, because in fact this window is 60 frames, and then it's being shifted one frame.
Okay.
So basically 59 frames are the same as per the previous prediction, so it cannot be that far.
In that case, you are sort of changing the pose, but in a very, very slight manner.
Yes, exactly.
So
yes.
you might still get this abrupt change because of some, but it is such a small in magnitude compared to the whole thing.
Yes,
okay.
exactly. And apart from that, one could apply some sort of smoothing filter on top of that. That's not uncommon.
And what is the audio about?
So the audio is basically in the data set, whatever human is performing. You can imagine this recording right now being an example from the data set. So I'm correcting my audio, and if there would be many cameras, we could collect my 3D pose.
Okay.
So it's you will see some examples, maybe it will become more clear. All right, now we can get to the actual experimental results. I'm sure you are very excited to see what kind of gestures my system can produce, but before we go into that, I want to tell you the data I used, because the model cannot do anything unless it has a data. And at the moment when I started my research, the only available data set was in Japan, and hence it was in Japanese. So I had to work with Japanese data. Thanks God I had also Japanese collaborators. And it's had some 3 hours of speech and 3D motion recorded in the motion capture lab. And now I want to show you some of the results. Audio doesn't really work. First of all, here you can see the example from the data set, what the actor actually have done. Here is the previous method, and here is our model. And let me try again and see if I can get sound. Well. You can see that the previous method was actually jumping quite a lot, as you were indicating, while our method was producing much more smoother motion. And we didn't stop there. We compared to another data set which was released recently, and this one was actually in English and had even more speech and 3D motion. And here we also applied it on actual virtual avatar as opposed to just stick figures. Yes, so that's kind of gestures my model can produce. It has been published this summer, so you can find the work online. The code is on GitHub, so if you feel like, you can play with that as well.